a universe spontaneously forming out of nothing as a result of quantum fluctuations, essentially, and then inflation making it grow, and it has essentially zero energy. But does it presuppose an existing set of laws of physics?
Well, that's, it's a good question. We were talking about it before this began, but what I wanted to point out, obviously, the answer is yes and no. because
the answer is yes.
It could be that all possible laws occur. It could be that all possible combinations of laws, multiverse doesn't have to be finite. It could be that every possibility that can happen happens, and therefore every possible set of laws of physics may exist, and that's the same, it seems to me, as having no laws. And basically, it's saying that there's no selection effect. It's just anything that can happen happens. But it could be, and in fact, in the case of string theory, there is some underlying law, and in fact, you didn't say it explicitly, but I'll say it. I assume quantum mechanics there. In order to have quantum fluctuations, one has to assume quantum mechanics. I don't know how to... I can only work with what I have as a physicist. There could, as far as I know, it's possible that quantum mechanics itself may not be universal. We don't have a fundamental law of physics. So the answer is, of course, one doesn't know. And not knowing is a wonderful thing. And so there may be a unique set of underlying laws in an 11-dimensional universe. There may be every possible set of laws in the universe in this multiverse that can happen. And my point is, therefore, that it's not as if you need... If we ask what people really mean when they ask, what's the miracle of existence? Most of the time they say, how can you get the stuff we have unless someone said, let there be whatever? And the point is, it's not a miracle to have stuff where there was no stuff. That's no miracle. It's not a miracle to have a universe where there was no universe. That's not a miracle. And you don't have to have a uniquely set of prescribed laws of physics for our universe to arise. Indeed, there may be some underlying law of physics in the universe, and I don't know the answer, but that doesn't... To me, the important question is, how did our universe get here? And, maybe I push this question, why is there something rather than nothing, back to the multiverse. I don't give a damn. It's not the thing that interests me. The interesting thing that interests me is, how did our universe get here? But it's an important question.
But even the multiverse, its existence is difficult to comprehend unless there's some underlying set of laws that allows it to...
But difficult to comprehend is different than existence. That's what's wonderful about physics, is that things that were difficult to comprehend happen. And we've been able to comprehend them. There may be ultimately things we'll never comprehend. I'm one of the people, I don't think we'll ever have a theory of everything. I would be amazed if we did. And I think that's the wonder and beauty of science. The mystery is what makes life worth living. And so, absolutely, I can't comprehend the words you're using. I can't comprehend mathematically, because I don't. If I could, I'd write it down in a physics paper. And so you're absolutely right. These are issues we don't understand, but they don't take away from the remarkable fact that it used to be that life was a miracle and had to demonstrate something beyond the laws of nature. Happily, Darwin got rid of that. And I would argue that physics is getting closer to the point of saying, at least to understand how our universe got into existence, we don't have to posit anything supernatural.
I'm ready.
Frank?
Lawrence.
Go ahead.
Okay, Lawrence, first of all, stellar performance. I'm sure the audience appreciated it. And for these...
Anyway, okay, thank you.
And since you're such a great supporter of the string theory community, I want to thank you for your comments.
I like to give you free advertising wherever I can.
Thank you very much. But my serious question is the following. You might be surprised, at least in my own personal views of physics, that I find a lot of resonance with what you say. And in particular, the whole question about whether the laws of physics themselves actually had some sort of natural selection to act upon them. Would you be surprised if I told you that I, in fact, accept that and have some minor evidence that that is true?
Well, I wouldn't be surprised. First of all, I don't think you should accept anything. That's really a key point. So you shouldn't believe anything.
Well, when I say accept, I mean provide my own internal proof.
Okay, if you could see evidence, then that's a good bit. There's lots of indirect evidence, and I happen to think the phenomenon of inflation is the best motivated evidence that there might be a multiverse. It's my opinion. But No, I wouldn't be surprised that if you agreed, because I've known you for a long time, and you're a sensible guy.
That sounds like a cop-out to me.
So when you're saying evidence, do you mean a prediction that we can test experimentally?
No, I do not.
You want to give it? I mean, everyone's wondering. So why don't you give it?
Well, actually, some of the people in this auditorium have actually heard a talk. Lawrence, I've been mucking around down in the mathematics of supersymmetry, and we have found these weird, and some people say unimportant, but evidence of what looks like error-correcting codes. There's only one place in nature, in the observed world that I know, where error-correcting codes occur, and that's in natural selection. And it's even not completely clear there, but there are, as you know, geneticists who make that argument.
I mean, it's fascinating. I'm skeptical, but it's it's great. I think it'll be amazing. I think what's amazing, and what I try to illustrate, is that we can even ask these questions. We could have had a symposium 30 years ago, a Nobel symposium, and we could have asked the questions, but we wouldn't have had any sensible. I mean, I'm not sure you'll argue that my answer is sensible, but we know so much more that we've gotten to the point where these questions are even discussed among scientists, which I find fascinating.
I think a lot of the issue that Alex was raising and many people raise in this connection is, what exactly do you mean by nothing?
Well, I thought I made it clear.
No, it was obviously not entirely clear. As you know, almost exactly 30 years ago, in fact, I made a proposal very much along the lines that you discussed here in Scientific American, with a rather precise, however, formulation of what nothing means. What I took as nothing is the idea that the universe would begin in a very, very symmetrical state with no matter and much more symmetry. The symmetries that are broken in our world would be restored. We know many of them are restored, so we could assume that there was a much more symmetrical state early on with, for instance, equal amounts of matter and antimatter. And then I think it was already plausible then, and it's become, as you mentioned, much more plausible now, that the laws we know operating on such a state could lead to something very much like our universe. But I wouldn't overstate how that means you're getting a universe from nothing. You're getting a universe from a framework of an assumption about what the initial state is and what the laws are. And both of those are certainly still up for grabs to a large extent, especially the assumption about what the initial state is, or even whether we should assume an initial state. For instance, one can sensibly speculate about whether that's the right formulation at all. Maybe the right formulation that would be more symmetrical would be to say something about the final state.
Yeah, no,
cosmology, as you know, is a subject that's changed a lot. You emphasize that, in fact. And I don't think it's over yet.
Well,
even at a very fundamental level.
Well, I think obviously I resonate with a lot of what you said, and I agree that one should be careful, as you should have been careful when you wrote the Scientific American article and and said, why is there something rather than nothing? Because nothing is unstable.
That's exactly what I said. Yeah.
And so we all use these terms, and what we mean, I think. Look, one can have a huge philosophical discussion about the nature of nothing. I think it's largely a waste of time myself. But what we operationally mean is that you might say nothing is non-existence. And the question is, how could you get something that exists now from something that didn't exist before? That's the weird thing. Now, whether there was absolutely nothing else is an interesting question, but it's not the question I think that one's addressing. How can you get something that exists when it didn't exist? And actually, that's no surprise. People seem to find it a surprise. Look at the light from the photons are coming from that light. Well, they were emitted spontaneously by electrons that jumped between levels in atoms. Did the photons exist before the electrons emitted them? Absolutely not. So they're photons that came into existence. It doesn't bother anybody. Somehow it bothers people when we talk about a universe. So you're absolutely right. One has to be careful. No. But I tried. No space is one version of nothing, but no particles, as you pointed out, is one version of nothing. But no space is a much more interesting version of nothing. No space and no time. And pointing out that even a space can come into existence when it wasn't is a fascinating thing to talk about. And maybe.
But I think you're overstating how much that can be done. You need something. You need a space out of which another. You can have more space arising out of some space.
No, I think you're. I think you're. No. Hold on a second.
It's very.
We agree that that a space-time which didn't exist, a four-dimensional closed universe, could come into existence that wasn't into existence before. You will agree with that statement.
But it doesn't start from nothing. It starts from a special initial.
But it doesn't start from a universe that existed before, because that universe wasn't there.
Well,
that's my point.
What you mean by a universe?
Well, the rest is semantics.
By nothing. No, it doesn't. It's.
Well. No, I mean, I think it's a remarkable thing that a universe can have zero. Well, you're not the only one who can interrupt, Frank. But it's a remarkable thing that a universe can have zero total energy and come into existence
no question.
That's all I wanted to point out.
That when Einstein first learned about that, he almost got himself run over by stopping in the middle of the street in Princeton.
Yeah. No, and so I think ultimately we're in a
striking observation. There's no question.
Yeah.
But I think the thing that confuses and upsets some people. And, well, in fact, I know it does. And
at least
not
one
me.
person.
It doesn't bother me. I don't care.
Oh, okay.
Except because of my sympathy for other people.
For humans.
But when you say nothing,
you said
it. That's you're threading your title. It means something to. It means different things to different people.
That's why I tried to find.
When I said nothing, I tried to be careful about what I meant by nothing.
So did I.
Well,
I defined three different versions of it. Anyway,
I think once you start talking about the laws being random or no laws at all, you could really start from nothing at all. I think that's going too far. I think that it's really within a specific framework that you can discuss these questions. And you definitely invoked quantum mechanics, you invoked relativity, you invoked a lot.
Absolutely. I gave an example by which the universe could come into existence, but I made a key point that we don't know.
Lawrence, what do you mean by exist?
Well, that's a good question. It means having a panel discussion. As a physicist, what existence means to me is that I can measure it, or not that I can measure, that Tara can measure it,
and
or
that's fine.
Someone else.
That's fine, but that does not exhaust the meaning of exist.
You're right, but it's all that I care about.
Okay.
Okay.
It's fine.
Okay. I mean, seriously, it's maybe my own limitation. Yeah. But if I can measure it, then as a scientist. And that, as a scientist, if I can't measure it even in principle, obviously we've all created, the theorists on the panel, things we can't measure. But in principle, we can imagine them being measured. And as a scientist, if it's not related to that, it's just not science.
Right. So I would like to sort of tie that with what Frank was just saying. And that is, 30 years ago, you couldn't have this discussion. And 30 more years, you're going to have a really different discussion. I mean, the fact is, we're putting in a lot of scientific cultural prejudice into our models, and it is true you can make up a model in which you get the universe we're living in today from a place that had no space and time and no particles and energy or something. That's perfectly a reasonable prescription you can kind of do. I've actually assigned it as a homework problem and have my students choose the coefficient of the area functions to get the universe of their design. But it's much more difficult to be arguing about how to remove the context and how to do that. Yes. And so this is where I have to voice my.
What do you mean how to remove the context?
Well, so one of the contexts that both of you talked about are the multiverses and the anthropic principle, and those are arguments about what's going on. But I can give you examples of universes that are much more probable than the one we live in, and examplos of universes infinitely more probable than we live in. Yeah. And therefore, it'd be great even though rare things happen, we shouldn't have happened, right?
No. Actually, that's the important thing. If it were really physics, it would be great. And one of my problems I've worried about multiverses is that if we had a theory that allowed us to calculate the probability distribution over universes, well, that would require having a theory of the multiverse, which we don't have. anyone who talks about probability distribution doesn't know what they're talking about because we don't have a theory yet. We can guess the probability.
Right, but if you're going to do the anthropic principle, you're immediately putting in probability distributions.
Well, you're
right?
assuming a selection effect, but you're assuming the probability distribution, but you don't. That's the problem with the anthropic principle, is it's always based on ignorance. Because if you really had a theory, you wouldn't have to use the anthropic principle anymore. You just calculate.
Right.
Lawrence, can I ask a really dumb question?
Yeah, I'm biting my tongue, but go ahead. Yes.
You agree that space and time come into existence, yes?
Probably. I wouldn't
It's happening
say
right now in this room.
No. I mean,
it's a serious question.
as you're well aware, there are models of bouncing universes that I find particularly ugly that go through something at which you have to do Planck scale physics. But you could have imagined an eternal universe that bounces. It doesn't obviate anything that I talked about.
But my point is, you talked about the dark matter particle going through the universe. In this space, it's expanding, right? And time is growing, right?
What? Where? The space between you and me isn't expanding.
Between my hands,
gravitation.
between us and the audience, right? It's just that gravitationally we got corrections going on.
Yeah, well,
but
it's
the
not
fact
expanding.
is, space is being created all the time, right?
Yeah, so?
So that was the question, right?
But if I could get back to my question, the point's much simpler. How do you have dynamics without time?
That's a wonderful question. I wish I had the answer. But, the point is, when people talk about, in fact, one of the arguments, look, I've just come from Australia where I was having this debate with a Christian apologist. And the argument given of cause and effect, that there had to be some purpose because there has to be, the cause and there has to be universal, the first mover, all the rest of the stuff. The point is, you're absolutely right. If time comes into existence at the same time as space, then the question of what happened before is not a good question.
It's not a scientific
It's not a scientific question. But I'm not sure it's not a scientific question. It's not a question we can answer yet because we don't have an understanding of that theory and how time can exist. I don't think you will agree with me that there's a vast difference between things we don't understand and things that are not understandable.
Oh, absolutely.
And so it's absolutely true that I can't, as a physicist now, adequately discuss what I mean by universes without time. But that doesn't mean that someday one of the young people sitting here won't.
No, but I'm just saying that's an obvious hole in the argument.
There's a what? That's a what?
That is, to me, the most obvious hole in the argument. I don't know how to talk about dynamics without time.
Well, you can imagine. You can. You can imagine. Well, you can imagine a super space, and I wasn't going to say superstring, argument where you have a Hamiltonian and things look like they're static, but locally they're dynamics when you take part of the system. You know how to do all that.
Yeah, but then you have a pre-existing space in which there are laws of physics.
Not space.
And you haven't.
You don't have our
space.
space.
But you have a pre-existing entity of some sort.
I don't care if there's a pre-existing entity. Our universe did not exist. It came into existence. That's the thing I wanted to discuss. And I don't see why people are worried about stuff we can't discuss. We can discuss possibly how our universe came into existence. Isn't that good enough to be celebrating on a nice afternoon in Minnesota?
I like it, but I want to know what happened beforehand.
Well, I would too, but I don't know.
I think we're all happy to celebrate the idea that we've progressed enormously in recent decades, and our understanding has pushed back the frontiers of what needs to be assumed as unexplained within our description of the universe. But I think it's far from the case that we pushed it all the way back to nothing.
Well, I think we're in agreement. Because the point and if you listen to carefully what I said and what I write, I never say we've pushed our understanding back to nothing. We've made certain postulates plausible, and that is fascinating. Darwin did not understand DNA or the mechanisms of genetic mutation when he developed natural selection. What he showed was eminently plausible based on the fossil record and what he knew, that all the diversity of life came from a single life form. We now know much more. And what's great, and what I really want to do, and I want to emphasize, is not overstate what we know, but the very fact that we can begin to address these questions should get people interested in thinking about them as scientists.
Maybe a position that I'm very comfortable with and have been for a long time, is that the ultimate laws that govern the universe, including both the laws and the initial conditions, or whatever substitutes for initial conditions in a final formulation, will turn out to be simple and beautiful. But it won't be 0 equals 0. It'll be something richer than that.
Well, that's nice, but that's much more speculative than anything I said. It's a nice idea, but
no, it's not.
We don't know it'll be simple and beautiful. I mean, it's nice. I'm glad it makes you happy. But,
I think it's what you're groping for.
But what's actually what's equally plausible, and I thought you were going to say, is that there may be no such thing as initial conditions. Initial conditions may be inseparable from final conditions, and their very question itself may be a bad question, and that's great. Yeah. That's great, and science will, and that may change the picture. Yeah.
Well, but we don't know yet.
We don't know yet. And let's celebrate.
And we're pushing things. We're pushing.
Well, I'm pushing you.
What's that? We're not pushing you. Okay, we'll try to pull you in.
I want to take a question from the audience and contextualize it a little bit. We've heard some talk about string theory not being physics because it's not testable.
I didn't say that.
Well, no, you would never say that. No, Jim's your friend. Is the multiverse theory physics? What this person is asking is, can we design or conceive of an experiment or set of experiments to explore the concept of the multiverse?
That's a really good question. Are we just talking metaphysics or is it physics? Is the multiverse physics? Because in principle, although it's possible in certain multiverse theories that universes can collide and then you'd know about it before you ended existence. But it could be that, and it's quite likely that if we're part of a multiverse, that we'll never have direct causal information about the rest. But I think it can be science in the following sense that atoms were science before we knew about them. Namely, before we could measure them directly. One could imagine that we did have a very good theory that explained why there are 3 generations of elementary particles, why the proton is 2,000 times heavier than the electron, et cetera, et cetera, et cetera, why gravity is much weaker than the other force. And it could be a corollary of that theory that, in fact, we can actually predict that inflation must have happened, for example. And then we can make 50 predictions we should compare with experiments. But one of the inevitable logical consequences of that theory is that there's a multiverse. So we can probe 49 aspects of that theory and test them, and then we're willing to say the one equally logical consequence that can't be removed also must exist. So I think that's science.
I agree very strongly with that. In fact, I think we have an extremely useful and profound example of a theory that's very rich in consequences that can't be verified, and that's quantum mechanics. Quantum mechanics works on wave functions that have much more information in them than we can extract even in principle. So,
yeah. Okay, we're in agreement.
Let me put forward one final question from the audience because I thought of it too during your talk. This idea that during the inflationary period we had sort of a closed universe, but it inflated so fast that what we measure appears to be flat. And the questioner wants to know, is our determination of the flatness due to our measurements, which you showed, it's really closed, but our measurements make us think it's flat because it inflated so fast?
It's obviously a good question. What we need to say, and we often need to be more precise, and me too, and we tend to say things. What we mean is that the measurable, observable universe is indistinguishable from a flat universe. But the definition of universe has changed, of course. The universe, what we mean by universe is now that which we are in causal contact with, or ever could be in causal contact with, or ever will be in causal contact with in the future. And that's not everything. And so if that picture I gave, which is one version, which is that a closed universe is created, if that's true, then on sufficiently large scales, that closed space-time is curved. But inflation generically, although not universally, but generically produces so much expansion that the difference between omega equal 1 is in the 50th decimal place or something. So if we waited in a universe that lasts forever, if you waited long enough, you might see some evidence for that, except in a universe that happens to be dominated by vacuum energy, all that information will never be recovered because the rest of the universe will disappear.
Okay, we will close now and reconvene at 3 o'clock for Father Coyne's talk.